All right, we'll continue the previous lecture. Last time we started chapter 12, fans and air distribution. Okay, so this chapter has two parts. One was fans and blower. The second part is ducting. We have discussed various aspects of the fan, and in this class we'll discuss ducting. Let's start from the definition. What is ducting? Ducting are the pipes or passages used in HVAC system to deliver and remove air. I mean, these are the passages or pipe that deliver air to conditioning space, and similarly, they take the conditions air from conditioned space to sometimes for recirculation or sometimes for exhaust. As you can see in this figure, we have different types of the ducting. One of them we call the makeup duct, right? So this is like a makeup duct, and then we have the supply duct, and then we have the return duct, and then the recirculation duct or the exhaust duct. So there are five possible kinds of the duct depending upon their location where it is installed. For example, the duct which is located after the fan, we call it as a supply duct, and those duct which takes the conditioned air, that's called the return air from the space. So we can have five possible ducts that are installed in HVAC system. Now in this figure you can see SA mean this is the supply air, right? SA is a supply air, right? This is the return air, and then this is the outside air, right? So as you can see, these are the two different zone. Let's say this is zone 1, this is zone 2. So the part of the duct which is supplying air, that's called the supply duct, right? And there is a main branch. This is called the main branch, and from main branch we have this branch one. This is the main duct. This is the branch duct. And similarly, the air which is taking from outside, that's called the makeup air, as I discuss here, makeup duct. So what are the different types of the duct? We can classify the duct by different way. One of the way of classification is based on the shape. We can have the rectangular or square duct. We can have the round duct or the oval duct. As you can see in this figure, we can have three possible shapes for the duct. This is a circular duct. We can have the oval duct or rectangular or square duct, right? So let's say this is a square one, this is a rectangular one, or there could be, I mean, this is called the connector one, or sometimes they are so called convergent duct, right? So there are three possible shapes of the duct. Normally the circular duct, they are manufactured for a small diameter pipe, and they're easy to manufacture. Similarly, this is for the medium size. Whereas when the size of the duct, I mean, requirement for the airflow rate is very high, that means the size of the duct required is too high. So then we prefer to have the rectangular duct. We can also classify the duct based on the pressure. I mean, there are low pressure duct, high pressure duct, and medium pressure duct and the high pressure duct. You can see depending upon the range of the pressure, I mean the fan static pressure. We discussed in previous class, there are three types of the pressure that are being discussed. One was the static pressure, then we have the velocity pressure, then we have the total pressure, which is the sum of the static pressure and the velocity pressure. So, I mean, this is based on the fan static pressure. If the fan static pressure is less than 3 inch of the water column, then it is under the low pressure duct. And if the pressure is between 3 to 6 inch of the water column, then that will be under medium pressure duct. And high pressure duct mean in between the 6 to 10 inch of the water column. I also discussed in the previous class that the pressure in the ducting is normally represented with either millimeter of the water column, I mean mm of WC, or inch of the WC. So normally these are the two units that are being used for the ducting system. Third way of classification of the duct is based on the velocity. There could be the high velocity duct or the low velocity duct. We say the low velocity duct is when the velocity ranges between 900 to 2000 fpm, foot per minute, right? If the velocity is greater than 2000 fpm, that will be under the high velocity duct. So there are three different way that are used to classify the duct depending upon the shape, depending upon the operating pressure, and depending upon the velocity. And the next important aspect of the ducting is the material that are used for the ducting. Basically, the selection of the material depend upon several factors. One of the factor is the availability of the material, right? The cost of the material and the time required for the fabrication. Normally, I mean, the mostly used material for the ducting is a galvanized iron. I mean, this is a standard material for the ducting, right? And this is mostly used in fabrication of the ducting material, right? They can be fabricated in all shape, round, square, but oval. So all of the shapes they can be easily manufactured with that kind of the material. As you can see, this is the galvanized iron that are used for fabricating the ducting materials. And the second type of the material that is being used for ducting is aluminium. Now, aluminium is not so common for the ducting material, right? Aluminium is not so common. The reason is the cost. I mean, the aluminium is expensive one compared to the galvanized iron. But sometimes it depends upon the location where you want to use the ducting. I mean, normally in case of the galvanized iron, with the passage of time, some part of the galvanized iron may rust. So because of the rusting, bacteria may grow inside that ducting, right? So if the bacteria is growing, and if that air is supplied in such a sensitive area, like a sensitive area mean the places like ICU, right, operation theater, or some other most vulnerable places where I mean the area is very sensitive to the bacteria. In those places we don't prefer to install the ducting made of the galvanized iron. So in that case, what will be the preferred material? The aluminium will be the preferred material because aluminium cannot be rusted. So aluminum ducting is used in such places. But for normal condition, this is uneconomical and superfluous to use the aluminum material in case of the galvanized iron. Okay, and the third material that is used for the ducting is a pre-insulated material, right? I mean, when you want to save the time and money, then what you do, you use a already fabricated sheet. I mean, sheet is made of two material. The inner is some insulated material, and the outer surface is made of the aluminium sometimes, right? So both sides they are, I mean, under the aluminium material. So these sheets are used to fabricate these ducting, right? It can save time and it can save money. And the next material that is very common for the ducting is a fabric material. As you can see, the fabric material they can use both for supplying the hot air as well as the cold air depending upon the application. But the fabric material they are not suitable for the high pressure air, right? I mean, this is very common nowadays because this is like a portable one. I mean, you can move this ducting very easily from place to place. I mean, compared to the ducting made of galvanized iron or made of aluminium, this type of ducting can easily be moved from one place to another place. I mean, this is flexible in mounting and dismounting, and this is like a portable type of the ducting material. Okay. And I mean, normally the length of the duct is very large. Normally, let's say even in at GIK, let's say if I gave you the example of the FME, I mean we have at FME one AHU unit, air handling unit, which is installed very near to LH3. So from that room, the air is supplied throughout the building, and you can imagine the length of the ducting. I mean, you know that when you manufacture ducting, the maximum length that you can manufacture nowadays, I mean, economically is normally the standard length is 5 feet, right? But the length of installation of the ducting is too large. So what you do, then you combine the 5 feet length with other component of the duct, and that joining is with the help of different joints. So normally three joints are used for the ducting. One of them we call the slip joint, then we have the drive slip, and then we have the flange joint. I hope you are familiar with these joints. They are very common. One of them is a slip joint. So you can see this is like the S shape, and this is like an S shape. So this is one end of the duct and the other end of the duct. So they are, I mean, hold within that joint. There is a drive slip as well. So this is like a C clamp, right? And then we have the flange as well. You're also familiar with the flange. Flange is connected with like one end of the um, duct is connected with this part, another one is connected with this part, and both are joined with a nut bolt arrangement. That's called the flange joint. So these three joints are used in the ducting to join the different length of the ducts. And the thickness of various thickness of the sheets they are being used in ducting. They use a term they call the gauge. As you can see, I mean they use a term, it's called the gauge. Gauge is basically the representation of the thickness of that sheet through which we are making the material. Like you can see it start from the 14 gauge up to 24 gauge. 14 gauge is more thicker than 24, although the number 24 is larger than 14, but 14 gauge is much thicker than the 24 gauges, right? Yeah, as you can see, most of it depending upon the length, you can see the different joint is mentioned, which joint should be used. If the thickness is this much, right? As you can see, both for the galvanized iron as well as for the iron. For example, up to maximum size of 300 millimeter, the galvanized sheet of 0.36, which is 24 gauge. This is equal to 24 G when 24 gauge will be used. Similarly, if this is the length, and for aluminium, the thickness should be, I mean, more compared to the galvanized iron. I mean, zero point 0.8 thickness means 22 gauge, right? And similarly, the different joint will be used to hold the ducting, to increase the length. Then we have airflow in the ducts. Just like we discussed the airflow in the fan, similarly, we can have the same fundamental laws that were discussed in the fan. The same fundamental laws can be applied in case of the ducting material as well. You know that this fundamental equation that this one, this is in terms of head, and each term has a unit of the length. This equation can be represented in three ways. That can be represented in the units of specific energy, that can be represented in terms of pressure, or it can be represented in terms of the head. So now let's say in most of the book in fluid mechanics as well, I mean the equation that has the form, normally the head is used, right? I mean the first term is the static head, the next one is the velocity head, then we have the elevation head. So similarly, this is before the fan and this is after the fan, but in after the fan we have to include the friction factor, friction loss, as well as the input power of the fan, and the elevation is there. Now if we want to analyze the duct, then we can ignore the pump input, as well as we can ignore the elevation. I mean, if we ignore, let's say, the elevation head terms, and assuming that no fan is present, then the above equation can be simplified as, like you can have, we will have the static head, the velocity head, and similarly the static head, the velocity head, and the loss factor. So from this, we can also further simplify, I mean, in terms of the total head, because the total head is the sum of the static head and the velocity head. So delta P0 naught mean the total head. Similarly, there is a total pressure, right? So we can represent, I mean, this is again the same form. So this is the static head. This is the velocity head. Similarly, static head at point 2, the velocity head at point 2, and the pressure loss due to friction. So we can further simplify. This is basically P01 mean the total pressure at point 1, total pressure at point 2, and the pressure loss due to friction. So from here, we can calculate the pressure loss by using this formula. We have discussed this formula in previous class, that this loss head can be calculated by using the Moody friction chart. We discussed in the previous chart that from Moody friction chart we can calculate the value of the LF, and then we can have the value of the delta PF. What about how to get the, I mean, we can have the total head if we know the velocity head. And how can we know the velocity head? We know the formula for the velocity head. I mean, for standard air standard condition, we know that the velocity head is equal to rho times V divided by this one. This is in the unit of the British unit, I mean inch of the water gauge. In terms of the SI unit, we do have the values equal to this one. So you can see we just need the value of the velocity, average velocity which is flowing through the duct. Similarly, if we know the average velocity which is flowing through the duct, we can have the value of the velocity head in British unit as well as velocity head in SI unit. So once we have the velocity head, right, and the pressure loss due to friction, then we can have, I mean, static pressure is from the gauge, right? So we can have the value of the total pressure, or the difference can give us the value of the pressure loss due to friction. And this is this figure 1220 is basically the representation of how the pressure is changing in a duct. As you can see, I mean, this is the air flow through a duct through various sections. For example, first the area is decreasing, then it has a constant area, right, and then this area is suddenly increasing. So you can see the behavior of the different pressure. For example, we are talking about the two pressure. One, this line is for the static pressure, whereas the upper line, this one is for the total pressure. I mean, total pressure means the sum of the velocity pressure as well as the static pressure. And this is the base pressure, I mean, the atmospheric pressure. So you can see how the pressure, how the two pressure, they are varying along the length of the duct as the air flows through the duct. As you can see, I mean, because of the friction, I mean, when the air flow through the duct, there is a friction. Because of that friction, I mean, the pressure loss due to friction is increasing. I mean, this term is increasing as the air flow through the term. So because of the friction, I mean, the static pressure is decreasing. As you can see, static pressure is decreasing. So the static pressure, even because of the decrease of the static pressure, the total pressure is also increasing up to here, right? So again, if there is now there is the convergent, right? Just like a convergent part. So because of the decrease in area, there is a sudden decrease in the pressure of the static pressure is suddenly decreased, as you can see, because of the decrease in the area, right? Similarly, but the velocity will increase. That's why the total pressure is not decreased so much. Only the impact of the friction is being taken, right? So that's why it's not so decreased. Similarly, if the area remains constant, then the only decrease will be uniform now. The only decrease will be because of the friction factor. So here the only decrease will be because the friction factor. But when it reaches here, again the area, now the area is suddenly increasing. So when the area is suddenly increasing, that means the pressure is suddenly, it will increase. So from here, suddenly the pressure, static pressure will increase, but the velocity will decrease, right? When the velocity will decrease, that means the total pressure will decrease. Again, there is a constant area, so only decrease will be because of the friction factor only. So that will be the decrease will be uniform now. So here the decrease is uniform because only decreases because of the friction factor. Similarly, along that length, after that the decrease is uniform. Similarly, the decrease is uniform. That means this portion the decrease is only because of the friction factor. But here between B and C and similarly D and E, the impact of the area reduction and area sudden increment that is being can be observed from this figure. And then the sizing of the duct. In terms of, we can also say the duct's design. There are different charts that are being used, and those charts are provided by the ASHRAE that are used to design the duct, right? These are the, as you can see the chart, this chart is provided by the ASHRAE, and this chart is basically used to size the duct, to design the duct. To design the duct, we need certain input. We should have certain input. One of the input that is required is the airflow rate. How much airflow rate is required in that zone, and that airflow rate is basically obtained from the cooling and heating load calculation. So that means if you know the flow rate of the air that is required in a certain zone, which is obtained from the cooling and heating load calculation, then if you know any of the other factor, let's say other factor mean maybe from fan or blower, if you know the velocity, any of the input, let's say velocity, or from the calculation, if you know the pressure drop, right? Delta P F. The pressure drop, pressure loss, which is as a result of the friction, which is also called the friction loss. Any of the two property, then you can size the duct. As you can see in this chart, at horizontal axis, we have the airflow rate, which is obtained from the heating and cooling load calculation. Whereas on the vertical axis, we have the friction loss in the, inch of the water per 100 feet of the duct length. So this is for 100 feet of the duct length. This is the friction loss in inch of the water column, right? And if you know, let's say you, if you know the pressure loss is, let's say 0.5, right? And if you know the flow rate, let's say flow rate is 500, so that means you can figure out a point where the two lines meet. So this is the point. So if you know these points, that means you can design the duct. As you can see, for example, if you draw a parallel line to this one, this parallel line is parallel to the 600, whereas 600 is basically the velocity, right? This is basically the velocity in FPM. As you can see, this is the velocity in FPM, foot per minute, right? So you can read the velocity at this point, as well as if you draw a line parallel to this one, right? This one, you can read this is the diameter. So as you can see, this is the 12 diameter, and diameter is given in inches. You can see this is the duct diameter. So you can figure out the diameter of the duct as well. So that's basically the design that you will use. If you know that this is the airflow rate and this is the pressure loss, then you can figure out a point on that graph. So you will see that the duct required is 12-inch duct diameter, right? And similarly, you can also calculate the velocity of the air that should be that can flow through that particular duct. This graph is for the British unit. Similarly, we have the graph for the SI unit. Now the air quantity that is basically represented in liter per second. The flow rate is liter per second at this density of air. Similarly, the friction loss and the pressure loss because of the friction is represented in Pascal per meter of the duct length, right? So again, you can have the velocity in meter per second and the duct diameter in meters, right? So this is now the duct diameter is represented in the millimeter. So these are basically the millimeter. Okay. Sometimes, you can see the dimensions of the duct that you have calculated from this graph, they are represented in diameter, right? They are represented in diameter, right? But normally, let's say you want to construct, or the availability of the duct is in the form of rectangular duct, right, or the square duct. So how to convert that equivalent diameter into rectangular or the square duct. Then ASHRAE has provided a chart for circular equivalent of rectangular duct for equal friction and capacity. So this is basically the empirical relation that can be used to convert the diameter. I mean, if you have a circular duct, let's say this is a circular duct, so how that circular duct will be equivalent to a square duct or a rectangular duct. So how can you convert? You can convert by using this table 12-7. Right, basically they have solved this empirical relation and they have obtained this relationship. For example, in the previous case, you calculated the diameter was 12, right? The diameter was given to be 12 inches, right? So what should be the equivalent length of the duct? Now you can see these are the diameter. All these are given here. These are the diameter. So let's say if you select any of the 12, let's say this is the 12.2. So you can have this combination which is equivalent to 12 inch of the diameter, let's say. So this will say that you can select this duct which has the height of 16 inch and the width of, let's say, 8 inch. So you can select 16 by 8 inch of duct, right, which is equivalent to this um, circular duct, right? So that means you can have 16 by 8 inch, right? I mean, you can have more than one combination as well. I mean, you can have more than one combination as well, depending upon the available space. I mean, sometimes when you install a duct on the roof, sometimes more height is available. Sometimes you install in such a place where the width is available, but height is very short. So for the same diameter, you can have more than one option. Let me give you an example. For example, let's say if you have let's say 18, let's say this is 18.2, so there will be another option for 18.2 as well. Let me see where is that option. Let's say this is very close to that, right? So that means you can use this combination or this combination. For example, if you use this combination, that means that duct will be equivalent to 20 by 14, right? That will be 20 by 14 inch duct, right? If you use this combination, that means you are going to use 30 by 30 by 10 inch, right? So depending upon the available space, for example, here that will be used when you have, I mean, according to the height and width. Similarly, sometimes you have more width but less height, so you can choose this combination. So this is an equivalent diameter for the rectangular duct. Then, I mean, when you connect one duct to another duct, there are different fitting that are being used. For example, let's say the straight duct was going, and then maybe you need one elbow, right, to change the direction of the flow, right? And then maybe you can have maybe some convergent, right? So there are different fittings that are being used in the ducting system. So broadly speaking, there are two types of the fitting for the ducting system. One we call the constant flow fitting. Right? This is a constant flow fitting. The example of the constant flow fitting is elbow or a transition, etc. And the second type of the fitting we call the divided flow fitting, like the Y fitting or the T fitting. Let me show you different fitting. For example, this is, I mean, the first one is the elbow. As you can see, this is 90-degree elbow, but this type of the fitting is called constant flow fitting. I mean, the same flow enters and same flow leaves from here. So the constant flow fitting. Similarly, this is a transition. I mean, this part has a more diameter or more width, and then there is a transition from the larger duct to the smaller duct by using a convergent piece, right? So this is a constant flow. The same flow, same mass which is entering here, the same mass is leaving here. This is a constant flow. Whereas in case of this is the divided flow. This is the fitting that's called the divided flow fitting. Right? This is a typical example of the Y. This is called Y. Right? This has a shape of a Y like this one, right? This is the shape of the wire. So this is not a constant flow fitting. This is a divided flow. I mean, the total flow is divided now. One is moving in the forward direction, another one is moving in this direction. So this is a divided flow fitting. And this is called a T because its shape is the resemblance with the T. This is called the T fitting. Right? Similarly, this is a divided flow fitting. Okay, so basically, when we compare the pressure loss, let's say there was a straight duct, so the pressure loss in a straight duct is a result of the friction, right? When we compare the pressure loss in a fitting, I mean pressure loss in a fitting mean, let's say pressure loss in an elbow, pressure loss in a transition, or pressure loss in a Y fitting, right? That is much larger than the loss compared to a straight duct. That's why, since the magnitude is much greater than the losses in the straight pipe or the straight duct, that's why these losses are called dynamic losses. So dynamic losses are the pressure losses which are as a result of the fitting. Right? So these are very prominent losses that you cannot ignore these losses, right? I mean, depending upon the types of the fitting, if you compare the 90-degree elbow compared with another elbow, which is, which has the smaller angle, right? So the friction factor changes. So you can calculate the value of the pressure loss, which is also called the dynamic losses, from the fitting by using this formula. So this formula is a function of a friction constant, right, which is also called the friction coefficient and the velocity head. Velocity head we just studied in the previous class, even in today's lecture as well. So velocity head is a function of velocity only. I mean, if you know the velocity, you can calculate the pressure head. What about the friction loss? Friction loss or the friction coefficient, it depends on the types of the fitting. For every fitting, the value of the C naught is different, right? Let me show you. For example, here you can see, we can have three types of the elbow. This is called the 90-degree elbow, right? This is a 60-degree elbow. Again, this is a 45-degree elbow. And the elbow, they are also represented with R by D. R is this one, this radius, right? This is the R, and D is the diameter or internal diameter of the elbow. So that ratio is called R by D ratio. So depending upon the angle and the diameter of the elbow, whether this is 4-inch diameter, in the bracket they have mentioned in millimeter, right? This is in the bracket the units are in millimeter, whereas outside the bracket the units are in inches. So if you know the angle of the elbow and the diameter of the elbow, you can have the value of the C naught. So what you need is you just need the value of the C naught for different types of the fitting. So this was an example of the elbow. Similarly, we can have different fitting. For example, this is also an elbow. As you can see, this is also an elbow, but this elbow, we called it as a vein. Veins are connected. So this is called veins elbow, right? This is called elbow metered with single thickness veins. So this is a rectangular type. For this type of the elbow, you need three parameters to get the value of the C naught. For example, you can see you need the value of the R, you need the value of the S, you need the value of the L. So what is small r? Small r is this one, this diameter from center to this point. Similarly, S is the entrance width or entrance diameter, right? L is this one. So if you know these three parameters, then you can have value of the friction coefficient or C naught, right? So we can have other fitting as well, as this is a rectangular duct elbow. So this is a rectangular elbow. So for rectangular elbow, what you need is you need the value of H as well as the W, right? So and the angle as well, right? This angle as well. So if you know three parameter, the angle, height, and the width, right? Then you can read the value of the C naught. For example, the first parameter, this one is basically the H by W, right? And this one is the angle. So for this different value of H by W and angle, you can have the value of the friction coefficient. Similarly, and this is a transition, right? This is a transition, but the rectangular one from smaller height to larger height. This is a transition. So for this type of, what you need is you need the outer dia A naught and the inner dia, I mean the inlet dia, right? I mean ratio of this area and the angle. This is the angle. This is the angle of the transition. So if you know these parameters, you can have the value of the C naught. Similarly, for other fittings, this is instead of the rectangular one, you may have this the round, from round to round. Right? Similarly, you need the value of the ratio of the area and that angle. Then you can have the value of the friction coefficient. Right? Similarly, these are the example of the conical converging bell mouth with the end wall, right? I mean, this is a connection entrance. This is called the entrance. So similarly, for this one, you need the value of the L and diameter. L is the thickness of that, right? And D is the diameter of that from this to this one, right? So then you can have the value of the C naught, and as well as this angle as well. You need to know the angle as well. So then you can have the value of the C naught, right? Similarly for this one. So to get the pressure losses from the fitting, you need to know two values. The PV is the velocity head, and the C naught. So C naught is depending upon the types of the fitting, as I have shown you various tables from where you can get the value of the C naught. Now this is the example of the divided fitting. I mean, this is a Y fitting. This is called the Y fitting. For Y fitting, what you need is you need to know the flow rate. For example, this is QC is the flow rate which is entering into the duct, and this is supply, right? This is the branch one, right? B for branch. This is the main supply, right? So let's say if you want to know the value of the C naught, that let's say this is C naught, so it will be represented with let's say B for branch, let's say CB for branch, and for this is the main supply, let's say this is for CS, right? So let's say the first table is for the branch one, right? So branch one. So what you need is you need the ratio of the QB to the QC as well as the ratio of the area between them. So AB divided by AC, the ratio of the area as well as the ratio of the flow rate. Then you can have the value of the CB. Right? Similarly, if you want to get for the main supply duct instead of the branch duct, I mean, again, you need to know the ratio of the area, the ratio of the flow rate. Then you can have the value of the friction coefficient. Similarly for the T as well. So same formula applies for that. You need to know the two parameter. One is the main supply duct, another one is the branch duct. Right? For main supply duct, what you need is you need the ratio of the flow rate as well as the ratio of the areas. Then you can have the value of the friction coefficient. Similarly for the branch one, right? Okay, let me give you an example. This is example 12-7. So it says compute the lost pressure in a 6-inch 90-degree plated elbow. So this is a 90-degree elbow and the diameter is a 6-inch, right? 90-degree elbow, and the flow rate of that from flowing through that elbow is 150 CFM, right? Cubic feet per minute of the air. The ratio of the turning radius to the diameter is 1.5. I mean, R by capital D is 1.5, right? So you can assume the air standard assumption. So you need to know the lost pressure. So how can you calculate the lost pressure as a result of an elbow? So the loss pressure as a result of an elbow, as I mentioned previously, that is basically delta P because of the that's basically the C naught into PV. PV is the velocity pressure, right? So C naught basically depends upon the types of the fitting, and P naught PV we already calculated that. For this one we need the velocity. So velocity is already given, which is 150. So I think no problem to get this value. I mean, PV, we can easily put that value 150, so we can have the value of the PV. So how to get the value of the C naught? So that depends on the types of the fitting. So we are given that the diameter is 6-inch, that's a 90-degree elbow, and R by D is 1.5. So from the previous table that I showed you, This was the table. So that means this is a 90-degree elbow, and this ratio is 1.5, and the diameter of that elbow is a 6 inch. So this is a 6 inch, right? So 6 inch, and the angle is 90-degree. So that means this is the value of the C naught, right? So C naught is 0.43. So we can put all of the values, right? So what will be the V? I mean the average velocity. So from flow rate we can have, from flow rate we can get the value of Q naught by A. So Q naught is 150 cubic feet per minute, and then with the help of the area, which is pi by 4 d square, so we can have the velocity. So once we have velocity, we can put the values here. Then the C naught is 0.43 into the velocity, and then we can calculate the loss of the pressure, delta P naught. Okay, this is the loss in pressure because of the elbow, which is 90-degree elbow. Okay. Now there is another way. You can analyze the effect of fittings in terms of equivalent length, right? I mean, let's say if we have a fitting, let's say the fitting is elbow, right? This fitting is an elbow. So this elbow can have the same effect as the effect of the straight length. I mean, this is a straight length elbow, a straight length duct, and this is the elbow of a duct. So they can be equivalent. Although let's say the length of let's say the pressure loss created by that elbow is, let's say, it can have certain value. So the same pressure can be equated with the help of an equivalent length, but this equivalent length will be much larger because the pressure loss created by an elbow compared to that straight duct is much higher. So that's why when you will equate in terms of the length, then this length will be much larger. I mean, let's say the elbow creates a pressure loss, let's say 0.05 inch of water gauge, let's say WG. So this is the pressure loss that is created by an elbow. So same pressure loss can be created by the straight duct, but that length will be much larger for the same pressure loss. So that's called the equivalent length, right? So that equivalent length, can be calculated with the help of the table that is provided by the ASHRAE. As you can see, it depends upon the types of the fitting. Let's say the elbow can have the equivalent length compared to the straight duct. And I mean, there are different fitting. For example, this is the elbow. For elbow, there are different variation. Right, elbow can be 90-degree, 45-degree, right? The metered or the metered with veins I showed you in the previous slide. Similarly, there could be transition. Transition could be from convergent, and the transition could be divergent, right? It could be from round to round. It could be from rectangular to rectangular. So there are different transitions. Similarly, the entrance, there are different varieties of the entrance. Similarly, depending upon the branch could be T branch or it could be Y branch, or the similarly, right? Similarly, the branch fitting could be the, we can have the different option. So for each of the option, the value of the equivalent length is different, right? Equivalent length is different. For example, let's say I'm just giving you an example. Let's say if there is, let me give you an example. Let's say for elbow, let's say if we have this elbow, 90-degree elbow, right? And the diameter of the elbow is, let's say, 6 inch. Let's say this is an elbow, right? This is an elbow, and the diameter is a 6 inch, right? 6 inch, and I want to have the equivalent length. So equivalent length, let's say this is 90-degree. So the equivalent length is like 30 inch, right? So sorry, equivalent length is in feet. So 30 feet. I mean, if there is an elbow which is of 90-degree and 6 inch diameter, that will be equivalent to 30 feet of a straight duct. So 30 feet is a huge length compared to this small 90-degree elbow, right? So I hope you understand that. Then how can we have the equivalent length that will have the same pressure loss due to friction as this elbow? I mean, the same pressure loss by the straight duct will have the equivalent pressure drop because of friction by this elbow, right? So we can have the equivalent length from this table. Okay, and with different diameter, we can have different friction factor. I mean, C naught. Okay. The last one is the duct design or the duct sizing. I showed you one of the graph previously where you can have the value of the diameter of the duct if you know any of the two parameter. One was the flow rate, another one was either the velocity or the pressure drop. So there are three different methods that are used for designing the duct. One of the method we call the equal friction method, right? This is the equal friction method. Another one we call the balance capacity method. The last one is the static regain method. This method required the computation. I mean, this is the, I mean, it converge, it moves. I mean, this is like a numerical ways. It required huge computation, and this is the rough estimation based upon the experience, right? Basically, in this class, we'll discuss the equal friction method. Equal friction method is very universal method. This is used for all types of the system, whether that is a constant flow system or a variable air velocity system. So that's why in this class, we'll discuss two approaches for implementation of the equal friction method for the duct design. So let's see how can we understand the equal friction method. I mean, equal friction method is based on one assumption. And what is that assumption? The assumption is that it says to use the same value of the friction loss per unit length of the duct. I mean, whatever is the length of the duct, it says that you have to use the constant value of the friction loss. I mean, friction loss. I mean, the value of the delta P. I mean, this is because of pressure loss because of the friction. You have to use the constant value, right? The value of that will be the constant throughout the length, right? This is the assumption of this method. So the mostly adopted method for this method is mostly adopted for supply duct, return duct, or the exhaust air duct for medium pressure up to 4 inch of water gauge. Depending upon the types of the duct, different value of that delta pf is used. So let's say if the duct is, let's say, low velocity duct and the medium pressure duct, then you can use the value of that delta pf 0.08 to 0.15 inch of the water gauge per 100 feet length of the duct, right? And the velocity range will be 900 to 2500 feet per minute, right? Similarly, if the duct is high velocity duct, then you have to use the value of the friction loss in between the 0.15 to zero point 0.6 inch of the water gauge per 100 feet of the duct length. And the velocity range should be, when we say the high velocity, so high velocity means 2500 to 4000 FPM. So depending upon the application, right? Depending upon the application, because we can have a numerous application. For each of the application, the velocity value is different. So depending upon the velocity, if the velocity is low, then we can have the value in between this one. I mean, if it is low and medium, then the this factor can be chosen in between this one. And similarly, for high velocity, we can have the value of the delta PF between in between this one. And how can we decide the velocity, whether the velocity is high or whether the velocity is low? It depends on the application. Similarly, I mean, there is a limitation for this method, equal friction method. This method is not recommended for large length of the main duct. Like in industrial application, normally the length of the main duct is very large. So because the pressure loss is not practically to be constant when the duct length is very large, right? For short, I mean, or for the medium duct length, we can assume the pressure loss to be remains constant, but when the length especially in the industrial application, if the length is very large, then this assumption is not suitable, right? And the velocity should be within the permissible range. And the table 7 from the ASHRAE that give you basically the permissible range. When we say the low velocity and medium velocity or the high velocity, so basically it depends on the application. As you can see, different application here. I mean, if the application is a residence application, then the maximum velocity should not be greater than 1000 for the main duct. And similarly for the branch duct, the maximum, I mean, this is for the supply in case of supply duct. Similarly for return duct, there are different range of the velocities, right? Similarly, let's say I'm sitting in office. So let's say this is a private office. So in case of private office, the velocity should not be more than 2000, right, of the main duct. And if it is a return duct, it should not be more than 1500. And similarly for the branches duct. So this is the velocity, right? So based on that velocity, let's say, let's say 2000 mean this is under this one, the first range, right? So this is under the first range. So that means we can have the value of the delta PF any in between this one. Maybe we can have 0.1 because the velocity lies between 900 to 2500 FPM. So depending upon the velocity, depending upon the application, let's say here we have the industrial application. So industrial application mean the main supply is 3000. So 3000 is between the high velocity. So high velocity mean we have to take the constant value in between 0.15 to 0.6, right? So now let's try to calculate any of the duct, right? So let's say this is an application. I'm just assuming that this is an application of any private office. Let's say this is my office, FME building. So this is an FME building, and this is the requirement. Let's say this is the air handling unit. That air handling unit is supplying 5000 CFM, right? I mean cubic feet per minute. This is the flow rate. How do we know that the FME building requires a 5000 flow rate of the conditioned air? How we do? How we know that? Anyone? How do we know that this is the required conditioned air, the flow rate that is required? How do we know that? So no one is there.
यस सर सर वो प्रीवियस डिजाइन से हमें पता चलता है कि कितने ईयर चाहिए.
कहाँ से?
प्रीवियस मतलब डिजाइन की हमने जो कैलकुलेशन की होती है लोड कैलकुलेशन होगा.
हीटिंग और कूलिंग लोड कैलकुलेशन से. सो बेसिकली ये जो रिक्वायरमेंट है वी नो फ्रॉम द हीटिंग एंड कूलिंग लोड कैलकुलेशन से. So let's say air handling unit is supplying 5000 CFM. So this 5000 CFM, let's say, goes in the main branch. So let's say this is the first building, right? First building requirement is, let's say, 1000. So 1000 goes there, and then remaining is 4000. Right? So comes 4000 goes there, and then the second building comes. So 1000 is the demand of the second building. Then the remaining goes to be 3000. Then it goes to the next building. Then 1000 is the demand of the third building. Then the remaining 2000 goes there. Then the building 4, it has a demand of 1000. So 1000 goes there. So remaining is 1000. So let's say 1000 goes on. So fifth building has a demand of 500. And then similarly, the last building has a demand of 500. So total 5000 is divided in various buildings. But our target is based on the calculation of the heating and cooling load, although we know that this is the airflow rate. But next is how we design that duct, that what should be the size of this duct. So there are, I mean, one of the duct is the main supply duct. Let's say from here to here, right? That's called, let's say, A duct. Similarly, from here to here, we have, let's say, the B duct. Similarly, we have the C duct. Similarly, we have the D duct, right? D duct and E duct, let's say. Right? Similarly, we have the next duct. So we can have different, because if the flow rate is changes, then the diameter or the size of the duct may change. So how to calculate that? Let's say first I'm calculating from let's say for duct A. So there are two approaches for the equal friction method. This is the first method, equal friction method. So there are two approaches to solve the problem. The first approach is that you fix the pressure loss, right? I mean, let's say uh, based on what should be my delta PF? What do you think? What should be my delta PF? Any idea? What should be my delta PF? I mean, I have to take a constant one. I will assume that delta PF remains constant throughout. So what can I assume that the value? It depends on my application, right? So what is the application of that? The application is office building. So from previous table for the office building, as you can see, if there is a office building, so let's see where is that office building. So this is an office building. So for office building, the maximum velocity is 2000. So if the velocity is 2000, that means this is the application. So you can have the value of the delta PF in between the 0.08 to 0.15. So let's say I'm taking 0.8, right? So let's say I have assumed value to be 0.8, 0.8 inch of the water gauge per 100 feet of the duct length. So let's say I have assumed this pressure loss that will remain constant. So let's say what will be the size of the duct A. So we know I know the value of the delta PF and I know the airflow rate. I know the value of the airflow rate. So for duct A, the airflow rate is 5000, right? So 5000 and the delta PF is 0.08, right? So this is 0.08, right? So if you know two values, then I can have the size of the duct, right? By using the table that I have showed you previously. Let's say this is the table. So what is the value of the airflow rate for the duct A? The airflow rate is 5000. So this is the 5000. And what is the delta PF friction loss? 0.08. So this is the 0.08, right? And this is the 5000, right? So it cuts here. So at this point, I mean, parallel to that means 26. So 26 is the diameter of the duct, right? And similarly, I can have the velocity. I mean, parallel to this line. Parallel to this line, velocity is, I mean, 1400. I mean, I can give you exact value of the velocity, 1400. I mean, previously, we don't know the velocity. I just know the range of the velocity. I mean, I know that in private offices, the maximum velocity should be 2000. This is the maximum limit, but what exactly? So what exactly we can read from the table. So once we figure out the point, so from point we know that the diameter of the duct is 26 and the velocity is very close to 1400, 1400 um, feet per minute, right? So this is the size of the duct. Now this is in case of diameter. I mean, this is for the circular duct. Let's say you don't have in the market, the circular duct is not available. So what you need, you can have the rectangular or the square duct. You can use a table, which is the equivalent table of the circular duct to the rectangular duct. So let's say 26. So in this table, you can figure out 26. Where is 26? Then you can have the equivalent size. So let's say this is very close to 26. Right, this is also very close to 26, and there could be other combination as well. Depending upon the availability, you can have different value of the 26. I mean, this is also very close to 26. So let's say I'm taking this one 25.9. So that means the width should be 18 and the height should be 30. So this will be the duct that will be used. Let's say one is A, another one is B, right? One side is A of the rectangle and the other side is B, right? So for that case, let's say this is equal to 18 and this one is 30, right? So I can have the other combination as well for the same value of 26, very close to that, right? So I hope you understand that. This is the first approach, that how can you size that. Similarly, for next one, you can calculate that from, let's say, from here to here, what should be the size of the duct, right? So now we have the flow rate is 4,000 and the pressure is will remain constant throughout. So 4,000 and 0.08, you will again read the values. So where is 4,000? So this is 4,000, let's say, right? This is 4,000, let's say. So for now we will have the new line now. So the new line will cut here. So our new point is this one. So this is our new point. Now our new diameter is 24, next 24 inch, right? So next is 24-inch diameter. So that means here you have, I mean, here you have to put a convergent. You have to use a convergent. I mean, previously the duct is 26 inch, and then the next duct is 24, right? You need to put one convergent, right? Similarly, you can read the value of the velocity as well. So here the velocity will decrease because of the convergent, right? You can see, sorry, maybe velocity should increase. I think if you read that velocity, no, velocity should decrease. Yes. So this is the 1200. Okay. So similarly, you can get the value of the duct size for different branches, because even the in case of branches, you know the flow rate and you know the FPM, so you can read the value of the size of the duct both for the diameter, and then diameter can be converted into rectangular or the square duct. Yes.
सर कन्वर्जन की वजह से वेलोसिटी ज़्यादा नहीं होना चाहिए?
इसमें बेसिकली आई थिंक कन्वर्जन की वजह से या वेलोसिटी शुड बी हायर, but I think it says that the velocity is decreasing. If our point is the lower one, I mean, because the flow rate is reduced, right? It is because the flow rate is not the same one. I mean, flow rate is decreased. That's the only reason, because the same flow rate is not coming. I mean, the flow rate is decreased. Now the flow rate is because one part of the flow rate is given to here. Now the next, the flow rate is reduced. So for reduced flow rate, I think that's why the velocity is less. Okay. So similarly, you can have, I mean, for the next, the procedure is same. I think now you can calculate for each size, or even for the branches, you know the value of the delta PF and you know the flow rate, so you can calculate the diameter of the duct. Right? So this is the first approach. There is another approach as well, right? In second approach, what is the procedure? First of all, you have to select that part which has the maximum flow resistance, right? So first you have to check the maximum flow resistance. That maximum flow resistance will give you some approximation that this is the assumed value of the delta PF. I mean, because you have calculated from the maximum flow resistance. So that maximum flow resistance will give you some indication that what maximum possible resistance you can assume. Then you can calculate the duct equivalent length. I have explained how you can calculate the duct equivalent length, because an elbow can have an equivalent length to a straight duct. So you can have the equivalent duct length, right? So once you calculated that, then from the same table that I have showed you, same chart, you can calculate the size and diameter of the duct. Let me give you an example, then you will understand. For example, this is example 12-11. It says that size the duct system shown. So this is the duct system that have shown. So you need to size that duct using the equal friction method, right? It is given that total pressure available from the duct is 0.12 inch of the water gauge. The pressure drop for the each diffuser is 0.05. You know that the diffuser, they are installed inside the room. I mean, they are installed at the end, just like I'm sitting in my office. So at the top of the ceiling, there is a diffuser which supply the air to my room. So there is a pressure drop in the diffuser as well. So that 0.02 inch, but we'll just discuss the pressure drop in the main supply duct. So what's the procedure? The procedure is, first of all, you have to select the length which give you maximum flow resistance. So which length can give you the maximum flow resistance? I mean, this is, let's say, 6 meter. If we take this one, 6 meter plus 1.5, that will be not the maximum. If we count this one, this will not be the maximum. So the maximum one is 1, 2, 3. Right. So from main supply, when you supply that duct to this zone, right, so that will be the maximum resistance, right, maximum flow resistance. So first you can calculate this one, right? To calculate this one, you need to calculate the equivalent length. Equivalent length means this is the length of the straight duct. So this is 6 meter. So we have to calculate the equivalent length from the entrance. From the entrance, then we have this one is the y, and similarly this is again the y, and this is the elbow, right? Again this is an elbow, right? So we have how many fitting? One is the straight length, this is the straight length, no problem at all. Similarly this part is the straight length, no problem at all. This is a straight length, no problem at all. So straight length. So in addition to the straight length, we have to calculate the length for, let's say, for the entrance. So let's say L1, this is L1 is, let's say, 6 meter or 20 feet plus the entrance, right? So entrance plus the L1. Similarly, the next length is, let's say, 4.6 plus this one ST. I mean, that's the joining, right? And similarly, we can have the Y, I mean, equivalent length of the Y. Then we have the elbow, I mean, Y, then 45-degree elbow, and then we have the 90-degree elbow, and then finally this one, the connection, right? So you have to calculate the equivalent length. Let's say you put the values, let's say 20 plus this is the entrance. You can read from the previous table that I showed you that every fitting has a different equivalent length. So depending upon the type of the fitting, so you can put these values. For example, the next one is, let's say this one is 15 feet plus this one. So 15 feet plus the next one. So next one is, let's say, the 25 is 25, but remaining is the length of these fittings. So you have to add the length of the fitting, and then you can have the equivalent length. So once you have the equivalent length, then for, let's say, delta P naught is a 0.1. So you convert that per 100 feet. This equivalent length is 160. So what about for 100 feet? So you can have 0.063 inch of the water. So that means that maximum flow resistance is 0.063. So that means the assumption is okay. You can have the assumption of 0.1. So I mean, this is very close to that, right? So now you can calculate with the same procedure. Like, let's say we have different section. Let's say section 1. For section 1, we know that for section 1 we need two values. What we need is, we need the values of the flow rate, right? I mean Q. So Q is given. How can we calculate the flow rate here in the main branch? I mean, we know the flow rate here is 150. Here is a 200, and here is 150. So if we add up 150 plus 200 plus 150, so the main flow rate will be 500. So we know the flow rate here 500, and we know delta P naught into L, which is 0.058. I mean equivalent length. I mean, you calculated for section 1 the equivalent length, and then divided with this one, you can have 0.05. So once you have two values, this one flow rate and the loss friction, and from previous chart you can read the diameter of the duct and the velocity of the duct. Similarly for section 2, I mean, if it's 500, so out of 500, 150 will be in this branch, so the remaining flow at section 2 will be 350, right? So 350 is now the flow rate in that branch, and similarly it will have the value of the delta P naught by L, right, this one. And then from the table you can read the value of the duct diameter and the velocity. Similarly for other sections, so you can have the value of the duct diameter and the velocity if you know two values, delta P not divided by L, and similarly the flow rate. So then you can have the size in all of the five section, right? So this is the summary. I mean, let's say 1, 2, 3, how much is the total pressure? This is 1, 2, 3. You can add up all of the pressure drop. I mean, pressure drop in section 1 plus pressure drop in section 2 plus pressure drop in section 3. So that will give you total. Similarly, for this one, this is for this zone, it will be 1, 2, 4. So you can add up all of the pressure drop. That will give you the total pressure drop. Similarly, for this zone, that will be 1 and 5. So 1, 5 mean you can add up all of the pressure. That will give you the value of the total pressure drop. Okay. Okay, so that's the end of this chapter as well as your course, refrigeration and air conditioning. These are the suggested problem for chapter 12. These are very relevant to the fan calculation that we have discussed in the class as well as the ducting calculations. Okay. Finally, the discussion about the final exam. First of all, only the post midterm part will be considered in the final exam. You know that we have covered these chapter in the post mid. I'm in chapter 2, chapter 3, chapter 4, chapter 5, 6 and 8. They are basically as a one chapter actually, because the 5 is about the resistance or heat transfer through the building. Similarly, 6 and 8 is basically heating and cooling load. So they are basically connected ones. So I would say this is one chapter. Okay, and the lastly, we have the fan and ducting, chapter 12. So basically, I mean, from all of these, there will be one question. I mean, one question from this chapter 2, one question from chapter 3, one from chapter 4, one from this chapter, 4 question, and the lastly the fifth question. So there will be total 5 questions. So 5 questions mean 30% will be theory. I mean short question, just like you know my procedure, you know my style. That 30% will be that will be the short questions related to the theory, and 70% will be the numerical analysis, right? And I hope that you will get your complete pre-final results before 22nd January 2020. Right, so that's the end of this course. Thank you very much for your patience, and I hope you learned a lot from this course. If you have questions, you can